Let's start from something that until recently seemed like solid ground. In the world of particle physics, there's this concept called flavor symmetry. Basically, it's the idea that up and down quarks, those tiny building blocks of matter, are close enough in mass and behavior that you can treat them almost the same in most calculations. Not identical, but similar enough to make life easier for physicists. Think of it like two different flavors of ice cream that taste nearly the same: vanilla and French vanilla. Different, sure, but not in any way that usually matters. Now, fast forward to the present. CERN, home of the world's biggest particle smasher, just dropped a bombshell. The NA61/SHINE team ran a set of high-energy collisions using argon and scandium nuclei. And the results? Weird. Really weird. They noticed a significant break in this long-assumed flavor symmetry, like an 18% deviation in how certain particles, especially kaons, showed up. Not just a small tweak. This is the kind of result that makes physicists stop mid-coffee and ask, "What's that?" This isn't just about updating a spreadsheet or adding a footnote. If the results hold up under scrutiny, we may have to go back and question some of the core assumptions that guide how we understand matter itself. It could mean that the standard model, the big rulebook of particle physics, may be incomplete or missing something crucial. Or, even cooler, we might be brushing up against an entirely new frontier in physics. So buckle up. This isn't just a tweak in theory. It's the kind of discovery that could redraw the map. Before we dive into the freaky stuff, let's take a step back and talk about what quarks actually are. If you zoom into matter, way past atoms and electrons, you'll eventually get to the atomic nucleus. That's where protons and neutrons live, and they're the chunky core of every atom out there. But even these protons and neutrons aren't the end of the story. They're made of even smaller particles, quarks. There are 6 flavors of quarks: up, down, charm, strange, top, and bottom. Sounds like a weird ice cream shop, right? But for most of the everyday universe, the stuff we see, touch, and live in, it's really just about 2 of them, up and down quarks. Protons are made of 2 up quarks and 1 down quark, while neutrons are made of 2 down quarks and 1 up. That's it. That basic combo gives rise to the bulk of the matter in the universe. Now, these quarks don't just float around. They're held together by a force so insanely strong it's literally called the strong force. This force operates via particles called gluons, and the whole system is described by a theory called quantum chromodynamics, or QCD for short. Sounds complicated, and it is, but here's the kicker. It works. Or at least, it's worked pretty well, until now. So why does it matter that up and down quarks might not be as similar as we thought? Because everything we've built on QCD and the standard model rests on those assumptions. Shake them, and you shake the whole structure. Let's break this symmetry thing down. Imagine you're playing a video game where the main characters are red and blue warriors. They've got different armor, but the same skills, same health bars, same weapons. That's flavor symmetry in a nutshell. 2 particles that aren't identical, but close enough that the universe treats them more or less the same. In particle physics, flavor symmetry is the idea that up and down quarks should behave almost identically in nuclear reactions. Yes, the up quark is a tiny bit lighter than the down quark, but not enough to make a huge difference in most scenarios. So when physicists build models of nuclear behavior, they often just assume this symmetry to simplify their work. This idea has been incredibly useful. It helps in modeling particle collisions, predicting outcomes, and interpreting experimental results. If up and down quarks behave similarly, then we can reasonably expect certain reactions to produce roughly equal types of particles associated with them. But what if that fairness is an illusion? What if, under certain conditions, the universe starts showing clear preferences, treating one flavor better than the other? That's what this new CERN experiment seems to be pointing toward. So when flavor symmetry breaks, we're not just looking at a statistical hiccup. We're talking about a foundational shift in how we understand the most basic components of matter. Now here's where things get spicy. Meet the kaons, particles that are basically made up of a quark and an antiquark. More specifically, they usually involve one of our usual suspects, the up or down quark, paired with a strange quark. They're not the most common guests at the subatomic party, but when you slam atoms together at near light speed, like they do at CERN, kaons tend to show up whether you invited them or not. There are different types of kaons: positively charged, negatively charged, and neutral ones. Originally, physicists at NA61/Shine only planned to study the charged kaons. Why? Because the theory told them, hey, if you know how many positive and negative ones show up, you can pretty much guess how many neutral ones there should be. Flavor symmetry has your back. But just for kicks, or maybe a hunch, they decided to measure all the kaons, including the neutral ones. And boom, that's where things got weird. The numbers didn't add up. Not even close. Instead of the usual 2 to 3% wiggle room you'd expect if flavor symmetry were only slightly off, they saw a whopping 18% deviation. That's like baking a cake and ending up with an extra layer you didn't put in. This overproduction of charged kaons was a red flag. Something funky was definitely going on with the up and down quarks in those high-energy collisions. And it wasn't just a fluke, the data was solid. Flavor symmetry had just left the building. Now here's the twist that really has physicists scratching their heads. When you look at the argon and scandium nuclei used in the collisions, they're not perfectly balanced in terms of up and down quarks. Argon has 18 protons and 22 neutrons. Scandium has 21 protons and 24 neutrons. Do the math, and you realize these nuclei started off with more down quarks than up quarks. So, logically, if flavor symmetry breaks, you'd expect to see more particles involving down quarks popping out, right? But nope, the exact opposite happened. The final results showed more signs of up quark dominance. That's like flipping a coin weighted toward heads and getting tails over and over again. This flipped expectation is a big deal. It's not just that flavor symmetry broke, it broke in the wrong direction. It suggests there's something deeper going on here, some hidden mechanism at play that current theories haven't accounted for. And that's exciting, because science often moves forward not when things go as predicted, but when they don't. This unexpected bias challenges the very framework of how we interpret particle interactions. It's not just about rethinking a single experiment. It's about re-evaluating decades of theoretical assumptions. Here's where the implications get huge. The Standard Model has been the backbone of particle physics for decades. It's been tested, validated, and used to predict the outcomes of countless experiments. It describes how the basic particles interact through 3 of the 4 fundamental forces: electromagnetic, weak, and strong. But if the results from CERN's NA61/Shine experiment are correct, then the model may be missing a crucial piece. The flavor symmetry assumption is baked into a lot of calculations. Break that assumption, and things get messy. Some theorists are already thinking outside the box. Could there be unknown particles influencing the results? Could quarks behave differently when packed into larger nuclei? Or maybe we need an entirely new symmetry or force to explain the bias. Whatever the answer, it's clear that our current models might not be telling the whole story. We're not quite in throw out the textbooks territory yet, but we're definitely in check the appendix mode. Okay, so kaons are acting weird. Why should anyone outside a physics lab care? Because this is how revolutions in science begin. When experiments show something totally unexpected, it's often the first step toward deeper truths. Think about how weird Mercury's orbit looked until Einstein explained it with general relativity. Or how quantum mechanics arose from things classical physics just couldn't explain. This flavor symmetry breaking might lead to new physics, new particles, or even new ways of thinking about the universe. It might help explain why there's more matter than antimatter, or why dark matter doesn't seem to interact the way we expect. It could be one small crack that eventually leads us to a much bigger picture. So yeah, it's about kaons. But it's also about the next chapter in understanding the universe. In science, the most exciting phrase isn't eureka. It's "that's odd." What CERN found with these argon-scandium collisions is odd, very odd. But it's also incredibly promising. It's a sign that we might be missing something, and in science, missing something can be a good thing. It means there's more to discover, more to learn, and maybe a whole new frontier waiting just around the corner. The flavor symmetry break isn't the end of the story. It's the beginning of a mystery. And if history has taught us anything, it's that mysteries like this often lead to the most profound breakthroughs. So let's keep asking questions. Because when particles misbehave, the universe might just be trying to tell us something new.